So let's start the exercise questions. First question is, a discharge tube contains helium at low pressure. A large potential difference is applied across the tube. Consider helium atom that has just been ionized due to detachment of atomic electron. We need to find the ratio of the distance traveled by free electron to that by positive ion in short time interval after the ionization. So this is the first one. Let the charges be having charge Q, or let them be having charge E. So charge on the particles be E. Now we know that mass of electron is 9.1 into 10 to the power minus 31 kg. Mass of proton is 1.67 into 10 to the power minus 27 kg. Let the electric field be E. So force experienced by electron will be charge into electric field, and acceleration will be charge into electric field over the mass of electron, and displacement will be ut plus half at square. Initial velocity is 0, therefore only half at square. So a is this much and then t square. So small time interval dt square. Similarly, for positive ion, acceleration will be E over 4 into mass of protons, because in positive ions we have this much mass, this many particles. So displacement of positive ion will be, again initial velocity is 0, so ut is 0, so half a t square. So the ratio will be 4 mp over me. So once you put the value, you will get this ratio to be approximately 7340.6. Again, why did we put 4 here with mass of proton? Because in helium the nucleus consists of 2 protons and 2 neutrons. So the positive ion of helium consists of 2 protons, 2 neutrons. Therefore we are multiplying it with 4, 2 protons and 2 neutrons. In question 2, we have molecule of a gas filled in the discharge tube. It gets ionized when an electron is detached from it. Electric field is given. We need to find distance traveled by free electron in 1 microsecond, assuming no collision. If mean free path of electron is 1 mm, estimate the time of transit of free electron between successive collisions. So the second one, first of all, electric field is 5 kilovolt per meter, so 5 into 10 to the power 3 volt per meter. Time is 1 microsecond, that is 1 into 10 to the power minus 6 seconds. We know that force is equal to QE, charge into electric field. So charge is 1.6 into 10 to the power minus 19. Electric field is 5 into 10 to the power 3. So the force will be this much. Now acceleration will be force over mass, that is QE over mass of electron. So 1.6 into 10 to the power minus 16, because this 3 will get cancelled, into 5 over 9.1 into 10 to the power minus 31. So now let's find the things they have asked. First, the distance travelled. So initial velocity is 0, so only half at square will remain. So once you put the values, 1.6 into 10 to the power minus 16, so let's cancel them also. So we will have 9.1 into 10 to the power minus 15 into time square, so 1 into 10 to the power minus 6 whole square. So distance will be approximately 439.56 meters or approximately 440 meters. B part, D is 1 mm, that is 1 into 10 to the power 3 meters. So in this case the distance is 1 into 10 to the power minus 3, it is given half, then again acceleration 10 to the power 15 into t square. So from here t square will be 9.1 into 0.8 into 5 into 10 to the power minus 18. So t will be approximately equal to 1.508 into 10 to the power minus 9 second, or t will be approximately 1.5 nanosecond, because minus 9 is nano. In question 3 we have the mean free path of electron in a gas in a discharge tube inversely proportional to the pressure inside it. The Crookes dark space occupies half the length of the discharge tube when the pressure is 0.02 mm of mercury. So we need to estimate the pressure at which the dark space will fill the whole tube. So this one is the third one. So let's say that this is our discharge tube, these are our electrodes. So let's say this is anode, this is cathode. So let mean free path be L and pressure be P in the tube. Now we know that length is inversely proportional to pressure, and it is given length is half of the tube length, pressure is 0.02 mm of mercury. So as the pressure becomes half, L will double. So this means that initially L by 2 was filled. Understood this? L is inversely proportional to pressure. So if L pressure becomes half, if this becomes half, so this will become 2 times. So initially L by 2 was filled, so L will be filled finally, because it will become double, will be filled finally. So L will be filled, complete tube will be Crookes dark space in the complete tube. In question 4, two discharge tubes having identical material structure and same gas is filled in them. So the lengths are different, 10 centimeter and 20 centimeter. Sparking starts in both the tubes when potential between cathode and anode becomes 100 volt. If pressure in short tube is 1 mm of mercury, what is the pressure in the long tube? So this is the fourth one. So we know that volume can be potential is equal to pressure, it is proportional to pressure into the distance. So for let's say length ls, pl and ll. So we have two tubes, short and long. So this one is for short, this one is for long. So let's take the ratios. So ps ls over pl ll. So ultimately we know that it is 100 over 100 equal to 10 over 20. Now 1 mm over, let's say x, unknown x. So x will come out to be 1 over 2, that is 0.5 mm. In question 5, we need to calculate this ratio for tungsten emitter at different temperatures. N of T represents number of thermions emitted per second by surface at temperature T. Work function is given. So this one is the fifth one. So first of all, we know that current can be equal to NE, or N can be I over E. Now I can be written like T square e to the power minus 5 RT. Phi is 4.52 eV. K is 1.38 into 10 to the power minus 23 joule per Kelvin. KT. So N into 1000 AS 1000 square into e to the power minus 4.52 into 1.6 into 10 to the power minus 19 joule over 1.38 into 10 to the power minus 23 into 1000. So now it will be 1.7396 into 10 to the power minus 17. So first situation, when temperature is 300 Kelvin, so N of T over N of 1000 Kelvin will be AS E, then 300 square e to the power minus 1.6 into 10 to the power minus 19 over 1.38 to minus 23 into 300 over AS E into 1.73396 into 10 to the power minus 17. AS is also there. So after simplification, this ratio will be 7.05 into 10 to the power minus 55. Now second part, when temperature is 2000 Kelvin, so N T over N 1000 Kelvin same procedure. Now after simplifying this, you will get 9.51 into 10 to the power 11. Now C part, temperature 3000 Kelvin, completely same process. Yes, 3000 square into e to the power minus 4.52 into 1.6 into 10 to the power minus 19 over 1.38 into 10 to the power minus 23 into 3600 over as 1.396 into 10 to the power minus 17. So after simplification we will get 1.340 into 10 to the power 16. In question 6, the saturation current from thoriated tungsten cathode at 2000 Kelvin is given, which is 100 milliampere. What will be the saturation current for pure tungsten cathode of same surface area operating at same temperature? Constant A in Richardson-Dashman equation is given, and we need work function is also given for pure tungsten and thoriated tungsten. Sixth one, IAST square to the power minus 5 over KT. So I1 is I, A1 is 16 to 10 to the power 4, S1 is S, I2 is 100 milliampere, A2 is 3 into 10 to the power 4, S2 is same as, T2 is 2000 Kelvin, phi 2 is 2.6 eV, T1 is 2000, phi 1 is 4.5 eV, and obviously K is 1.38 into 10 to the power minus 23 joule per Kelvin. So I equal to 60 into 10 to the power 4 as 2000 whole square E minus 4.5 into 1.6 into 10 to the power minus 19 over 1.38 into 10 to the power minus 23 into 2000, that is 2 into 10 to the power 3. So 100 equal to 3 into 10 to the power 4 as 2000 square E minus 2.6 into 1.6 into 10 to the power minus 19 over 1.38 into 10 to the power minus 23 into 2 into 10 to the power 3. So we have these two equations. So dividing them, we will obtain e to the power minus 4.5 into 1.6 into 10 over 1.38 into 2 and minus 2.6 into 1.6 into 10 over 1.38 into 20. So after simplification, we will obtain I upon 100 equal to 20 into e to the power minus 11.014. So I over 100 will be 20 into 0.000016. So current will be 20 into 0.000016 into 100. So from here current will be 0.0329 milliampere or approximately 33 microampere. In question 7, a tungsten cathode and a thoriated tungsten cathode have same dimensions and they are operated at same temperature. Thoriated tungsten cathode gives 5000 times more current than other one. We need to find operating temperature and we can use the data from previous problem. So this is the 7th one. So what do we have? pure tungsten, thoriated tungsten. Phi is 4.5 eV. Here phi is 2.6 eV. A is 16 to 10 to the power 4 ampere per meter square per Kelvin square. Here A is 3 into 10 to the power 4. Now I is equal to A as T square E minus phi over KT. So it is given that current for thoriated tungsten is equal to 5000 times normal tungsten. So this means 5000 into S into 60 into 10 to the power 4 into T square e to the power minus 4.5 into 1.6 into 10 to the power minus 19 over 1.38 into 10 to the power minus 23 into T. So it will be S into 3 into 10 to the power 4 into T square e to the power minus 2.65 into 1.6 into 10 to the power minus 19 over 1.38 into 10 to the power minus 23 into T. So this 3 into 10 to the power 8 e to the power minus 4.5 into 1.6 to 10 to the power minus 19 over 1.38 into 10 to the power minus 23 into T equal to e to the power minus 2.65 into 1.6 into 10 to the power minus 19 over 1.38 into 10 to the power minus 23 into T into 3 into 10 to the power 4. So taking the natural log and simplifying, we will obtain this value. So T will be 22029 over 9.21. So it will be 2391.856 Kelvin. So this much temperature will be there.